Welcome, one and all, to the Cool Boards podcast with me, your host, David Kipping. Now, today's episode is going to be about gravitational waves. You know, it's often said that astronomy is the oldest of sciences, but for all that time, we have not been using gravitational waves, but rather we've been looking at the universe with light. For centuries, arguably even millennia, we've been looking up at the sky using light, electromagnetic radiation, and trying to understand the cosmos, trying to understand our place within it and where we come from and where it's all going. But throughout that entire time, all of our science of the universe has been based of photons, light, packets of light energy. Now, that's great. We've learned a huge amount about the universe thanks to light, but all of that light has to be ultimately emitted or reflected through some kind of electromagnetic process. But the universe doesn't just produce light, it does all sorts of wonderful things besides that. So that's why in 2015, a kind of historic, momentous thing happened. Humanity, for the first time, opened our eyes, or really even our gravitational ears, one might say, to a completely different way of understanding the universe, to listening to her. And that was from the first gravitational wave discovery, GW 1500914. So this was a pair of binary black holes that were merging together. It was an incredible discovery. Of course, we had long suspected black holes were numerous and many of them were out there, but to see them merge directly was a pretty amazing discovery in of itself. But I think for many of us, the more amazing thing was the detection of gravitational waves, a breakthrough into a new window into the universe. That was with the LIGO instrument. And for the last almost a decade now, we've had, 8 years of this science, we have been discovering now many dozens of these merging black hole and even neutron star events. That has been wonderful. We have learned a huge amount about the evolution and death throes of these compact objects. But at the same time, it's long been recognized there's a lot of stuff that LIGO can't see. And that's where my guest today comes in, because it is thought there is a completely different part of the spectrum, just how light has all of its different colors. We can see invisible light and there's infrared and radio. There are also different frequencies of gravitational waves. And so far, LIGO, as successful as it's been, has only been looking at one part of that spectrum. But there must be more. And in fact, there is surely more. And that especially comes with supermassive black holes, the cores of galaxies that are merging together. So my guest today is going to be diving into this topic with me, Professor Chiara Mingarelli. She's currently a professor at the University of Connecticut. She also has a joint appointment at the Flatiron Institute right in Manhattan, so kind of just down the road from where my office is. However, she will be moving soon to Yale University as a new professor during the faculty. Now, Chiara and I have known each other for a long time. I have a certain shared kinship with her, one might say, in terms of our science. Even though we work on very different things, we have both, throughout our careers, been looking for that which is just beyond the horizon. Both of us, myself with exomoons, her with this background gravitational wave signal from these supermassive black holes, we've both been looking for something which science predicted, but has been just beyond our fingertips technologically for so long. And yet, in her case especially, and well, also with exomoons, we are so close. We are just on the cusp now, finally, of breaking through. So we're going to go through that today. You're going to hear all about what is a gravitational wave? How are they produced? What makes them? What is the difference between what LIGO has seen, these binary merging signals, and what are these new types of signals that Chiara is particularly interested in finding, this background signal? So I hope you enjoy today's episode, and I'll see you at the end. Chiara, my first question for you is, what is a gravitational wave?
That's a great question. So a gravitational wave is a ripple in the fabric of space-time that travels at the speed of light. So this is one jumping off point where it's pretty good to explain what the difference is between Einstein's theory of gravity and the more traditional Newtonian theory of gravity. So in Newton's theory, you have two bodies with mass that attract each other because that's gravity, that attraction. In Einstein's theory, anything that has mass curves the space-time around it, and that curvature is gravity. And so that curvature means that the space-time that we live in is flexible and it can undulate like a wave. And so you can imagine something like the surface of the ocean with waves going across it. And in our universe, those space-time waves are called gravitational waves.
So when you often see people talk about this space-time curvature, and they often get like a tablecloth or something, right? And they pull it taut, and they put a heavy mass in the middle, and you see the sheet bend, which is space-time.
Yeah.
But that's not really a wave, right? But that's maybe what most people have in mind when they imagine this space-time curvature. That's probably the typical level of understanding.
Yeah.
But how does that static bend change from just being static to some kind of undulation that's propagating through this sheet? How do we go to that?
Well, there's two ways to think about this. So I've done this tabletop experiment, and I had this piece of stretchy lycra with a grid painted on it, right? And you put your heavy mass in the middle, as you explained. One way to think about just how the space-time fabric responds to masses is now to imagine, letting a ball bearing or something very heavy circle the central object. The central object, even though it's heavy, is going to move a little bit because that fabric is also moving a little bit in response to the ball bearing circling in and eventually plummeting to the center of that little gravitational well that you've created. So even in that very simple experiment, you can see that that fabric can carry information, right? It can transmit the fact that there's a wobble happening further away. But now if we talk about the space-time fabric in terms of gravitational waves and that undulation, as you mentioned, you can think about black holes that are starting to merge. And what they're doing is that they're moving through this space-time fabric. And as they plow through it and orbit each other faster and faster and faster, they're losing energy to this gravitational wave emission that they're creating. And so those waves that come from these two big black holes, which you can think of something like whales jumping in the ocean, right? Just creating these massive waves and those ripples going out in all directions. Those can eventually be detected here at the Earth.
So anything, you mentioned black holes. That's obviously the example, maybe if anyone's heard of gravitational wave detection, that's probably the context they've heard of it in, because we heard, 2015, LIGO, this amazing experiment that detected the first ever evidence of merging black holes, and it was the gravitational waves that they saw. But black holes are a special kind of object, right? They're almost like a hole that's been punched in space-time. Is this limited to just black holes? Is there something special about black holes in this story, or would planets do this? Do stars do this? Why is it that we always seem to be talking about black holes when we're talking about gravitational waves?
So black holes have a special place in the heart of anyone that studies gravitational waves, because black holes can remain as rigid objects very, very deep into their merger process. So anything that has a mass and can be accelerating around something else with the mass will create a gravitational wave. Even if I just by myself am spinning around and I'm asymmetric, I can create gravitational waves, but they're too weak to be detected. So stars can also emit gravitational waves. They're very weak because stars are very fluffy. So if you think about little small hard objects, something like a black hole that's very dense and very small compared to its mass, those are the perfect targets for gravitational wave progenitors. So the gravitational waves will more easily come out of the system because you have very massive objects that can get really close to each other before merging.
So if I had a pair of black holes, or even a pair of neutron stars, or whatever it is, a pair of two objects coming together, and it's creating ripples in space-time as it moves along this tablecloth, what determines the strength of that gravitational wave, and what determines the the frequency? Because waves normally have a frequency that we associate with them. So how does the conditions, the parameters of that particular setup affect the gravitational waves?
Right. That's a great question. So the strength of the gravitational wave, in our jargon, we call it the strain, but it's really just how powerful the signal is. So that's a strong function of how massive your system is. So
is it linear? If you double the mass?
Okay, I was going to say it scales like the chirp mass to the 5/3.
Okay, so that's...
I just didn't know if I was allowed to say that or not.
That's almost a quadratic scaling, right? So if you double it, you'd almost get 4 times, but not quite the strain.
Right. Yeah, right. That's right.
That's maybe a simpler way of approximating that.
Yeah, exactly.
So you were like, should I say this?
Exactly.
But yeah, our audience can handle that.
Okay, good. Yes, it's a very strong function of the mass. And so black holes being very massive are very, very solid targets for gravitational wave emission. And so now frequency is interesting because this is where things in astronomy become interesting, because the frequency is related to the period of the objects. And so very wide binary periods produce low frequency gravitational waves. And as the frequency increases, it's due to Kepler's laws and your binary shrinking. And so then you can eventually get into this very tight orbit. So the reason that I said earlier that we really like black holes that can get close to each other to emit gravitational waves is, number one, the strength of the gravitational waves gets much larger as the black holes get closer together. But then number two, we have experiments on the Earth that can detect a very narrow window of gravitational wave frequency. And that frequency is designed to capture the last few orbits or a fraction of an orbit of a binary black hole merger. And so they need to be very close together, making very strong gravitational waves for them to be detectable by LIGO here on the Earth.
So let me guess right. So the frequency basically increases as the binary gets closer and closer towards each other. So if this was like a chord or a sound, a note being played on an instrument, the pitch would go up as the merger gets closer and closer towards spiraling into each other.
I feel like you're trying to trigger me to do the sound, the spiral sound, which I will happily make. If you could listen to a binary black hole merger, the sound that you could hear, if you could hear gravitational waves, would go like this. Whoop. With the final thing at the end being the chirp where they're merging.
And that's when they collide, basically.
Exactly. Point. Yeah.
Okay, so the frequency is obviously related. There must be, so we have these experiments on Earth that are detecting these. The most famous one, probably, if you've heard of any of this, is probably LIGO.
That's
which has detected, dozens of these events, hundreds of these events at this point?
Almost 100. The 4th observing run just started. So far they've had 3 observing runs.
That's amazing.
Yes, I think many, many, many more will be measured soon.
So maybe you could, I know this is not the experiment you work on.
That's right.
But maybe you can just give us some context, give us a quick sense as to how LIGO detects gravitational waves.
Sure. So the way that LIGO works is that you have an experiment that takes an incoming laser beam and splits it into 2. And each half of this laser beam propagates out at a 90-degree angle. And so what happens is that and then the laser beams hit a mirror and then they come back and they recombine at the original point. Now, if your arms in this object called an interferometer, if your arms are the exact same length, when the beam recombines with itself, it will interfere destructively. So the peaks and the troughs will cancel each other. You don't see any signal at all. But gravitational waves change the distances between objects. And so as a gravitational wave transits through this detector, one arm gets a little bit longer than the other arm, and then vice versa. And they do this little arm dance, the gravitational wave dance, where one is contracting while the other one is getting longer, and then vice versa. The other arm contracts and the other one gets longer. And so this creates a signal that you can measure.
Okay, so we have these 2 arms which we're using, and we're basically literally seeing the distance on Earth, the space itself stretch, and that's how we detect. That's kind of because it must change your mindset, the way you think about living on Earth, knowing that your body, your atoms, right, are being constantly jiggling back and forth.
Yeah, they're constantly stretching and squashing. And this detector can actually give you a way of seeing it with light, because light will always travel at the speed of light. Even if a gravitational wave is going through it, like light is traveling at the speed of light. And so your arms are like these meter sticks that help you to understand how the distance is changing, one relative to the other. And this change is so small. It's the fraction of the size of a proton over 3 miles or 5 kilometers. So it's very, very, very small.
Now, given these waves travel, often from, across from other galaxies, right? These are often extragalactic signals that we're detecting. The universe is, of course, incredibly vast. So we can imagine in one particular galaxy, there is almost like a big stone, this black hole that's moving around on this tablecloth, and it's creating this wave that we detect. But it's surely not the only thing that's moving in the universe. The universe is full of moving stuff. And so this simple idea we might have seems like it's missing something, right? This sheet, like if I had a lake or a pond and I dropped one stone in it, you'd get one ripple. But that's not really what's happening, right? It's almost like raindrops all over this. There must be stuff happening all over the universe, all over the galaxies. And what does LIGO see this? Does it see a constant barrage of signals, or is it missing some extra signals that it's yet to detect?
So something that you're describing is called a gravitational wave background. And so this is the superposition of all of these gravitational wave signals that are happening at a similar frequency. So in the detector, you have this buildup of all of these signals, and there's so many of them that you can't tell one from the other. So this creates what we call a gravitational wave background. In the LIGO band, at very high frequencies, this hasn't been detected yet, because the mergers happen on such short timescales that they're just really little bursts of gravitational waves that you see. They don't really spend enough time, and there aren't enough simultaneous ones happening for there to be the buildup.
So it's just like a few seconds, that's all you get?
It's even a fraction of a second of signal that you see.
Yeah.
And so there's not enough signals at any one time to create that background yet.
But before then, it was still making a gravitational wave. It's just that wasn't detectable. Right?
That's right.
Yeah.
That's right.
It was too low a pitch almost, or too low a volume level for it to pick up.
That's right. The volume was too low.
Okay.
Exactly.
Right.
But as we develop more sophisticated instruments, then we can dig in, go down to lower frequencies and find things at lower volumes. And so as we do that, then I think we'll be able to start seeing more of a stochastic background in the LIGO band at the relatively high frequencies. So one thing that we haven't touched on yet that might be useful is the whole frequency range of gravitational waves that you can detect. I think in terms of astronomy, we're really used to thinking about the wavelengths of light and the optical, which you can see with your eyes, and then you have
like hundreds of nanometers, sort of like tiny, tiny scales. Yeah.
Exactly. Now, with gravitational waves, it's a completely different kind of spectrum. So it has nothing to do with light at all. When I was first starting to study gravitational waves, this really blew my mind, because when you think of astronomy, you think, okay, I have infrared radiation, I have optical radiation, UV, X-ray, whatever you want. This has absolutely nothing to do with light. This is the fabric of space-time itself that moves, and the frequency of that motion, which is, for me, it was so mind-blowing to think that there's a completely independent spectrum. And sometimes we call it gravitational radiation, an analogy with electromagnetic radiation or light. And so LIGO is very sensitive to high-frequency gravitational waves. But
so those chirps, basically.
Those chirps, exactly. And it's so high frequency that if we could hear gravitational waves, there's a one-to-one mapping to the human audio band, which is a really neat thing. That's just a complete coincidence, but you could actually hear the gravitational waves that LIGO hears if your ears were gravitational wave detectors.
That effect you did of the whoop, that was actually pretty close to what we would hear.
You would, exactly. You would hear the whoop.
You weren't kidding.
No, not joking. That is for real what it would sound like at those frequencies. And so then it makes sense to think, there's all of these different processes that are happening, as you mentioned, in different galaxies far away in the universe. Well, what else is happening? Well, there's actually tons of stuff happening at different frequencies. And so we have no way right now of accessing the middle range frequency where you would have very small, supermassive black holes that are merging.
Hold on, small, supermassive.
Yes,
That sounds like an oxymoron. What do you mean by that?
I fondly call them baby supermassive black holes.
Okay.
They are about 100,000 to 1,000,000 times the mass of the sun. So similar to Sagittarius A star that's at the center of our galaxy. These are very small supermassive black holes. They barely made it to supermassive black hole, but they are there. But they're small. That's okay. And they merge with other supermassive black holes. But the largest gravitational waves are created by the mergers of supermassive black holes that are 1 billion times the mass of the sun. So 1,000 times more massive than anything that's at the center of our galaxy.
It's like kind of like gargantuan from Interstellar. Right?
Exactly, Gargantua.
Yeah.
That's yes, exactly. That kind of black hole is what I'm really curious about investigating. Now, those black holes, when they merge with other similar black holes, create gravitational waves that are 1,000,000 times more powerful than what LIGO has seen so far. But they're rare because those supermassive black holes live in the centers of galaxies. And so you need a galaxy merger to create that kind of supermassive black hole merger. And so while the signals are much, much more powerful, they're rare. But we win in the sense that these signals are so powerful that you can start detecting them 25 million years before they merge. And so with LIGO, you have black holes that are maybe 10 to 100 times the mass of the sun, and they're merging. And you see them at high frequency a fraction of a second before they merge. But with these very low frequency gravitational wave sources from supermassive black holes, we detect them with a different experiment that we can talk about in a second called pulsar timing arrays. With those, they are in our detector for 25 million years. So they're very slow in spiraling.
So it's like a constant static hum almost from this, where versus the short, sharp, someone shouting just for a brief moment, which you get with small black holes. These guys, they're just constantly screaming at almost a very loud but a lower frequency. Is that right?
Right, like a tenor holding a note, right?
Yeah,
at the end of an opera, just kind of hanging out there for an incredibly long time. Exactly. And so supermassive black holes are amazing. And because they spend so much time merging, then you can start to have multiple mergers happening at the same time, even though they're very rare. The fact that they take so long to merge means that there's enough of them at any particular frequency in our detector to create a gravitational wave background. And so pulsar timing array experiments that go after these supermassive black holes are first signal that we ever wanted to find was the gravitational wave background, because that should, for us, be the loudest signal. Whereas LIGO at higher frequencies is always looking for those, little quick chirps from the final shout from these stellar mass black hole mergers.
So yeah, let's talk about how we detect those then. So you mentioned this, that LIGO cannot see the most extreme merging events we can imagine of Gargantua merging into another Gargantua.
Yeah.
And yet we believe these things should be happening more or less as a process of, otherwise how do you make such big black holes, right? There must be a process of merging of smaller black holes to eventually get to the big ones. And yet obviously LIGO can't see them because the frequency is just out of its range. So that's a problem, right? Because if the frequency is low, that means the wavelength is kind of reciprocal, is very, 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 very long. And presumably LIGO just physically is too small to see those wavelengths. How could you have a detector bigger than the Earth though? Like how do we get those very, very low frequencies?
Oh, I'm so glad you asked me this question. I mean, it's the perfect
This is your passion project right here. Yeah.
I mean, this is what it's all about. So you're right. These black holes have, when they're creating gravitational waves, they have periods of decades, right? Or their wavelengths are light years long, which is really incredible to think about. And so you can't build a detector on the Earth.
A ripple in space-time that's light years across.
Light years long,
wow.
Exactly. So it's really incredible. So you can't build a detector on the Earth that that detects this. So what we do is that we use pulsars in our galaxy to look for these signals. So a pulsar is a neutron star that has its spin axis misaligned with its magnetic field axis. And so every time it spins around, it's like a lighthouse. It sends a flash of radio waves. And so it does this with such amount of precision that you can time them down to better than 100 nanoseconds over a decade. Right? That's 1 part in a million billion.
So like almost like atomic clocks, like they're the most precise clocks.
That's right. Until 2012, they were better than atomic clocks, but then the atomic clocks caught up and now they're better, which is fair, right? That's good.
Yeah.
But
you don't have atomic clocks on Alpha Centauri though, so this is kind of, it's no point for you. There's no value to that. You want atomic clocks all over the universe.
Exactly. And so within our own galaxy, we have all of these pulsars that have incredible timing. And so if we go back to when we first started our chat, we were talking about what is a gravitational wave. Well, it changes the distances between objects. It's a ripple on the fabric of space-time. And so these ultra-stable clocks with these gravitational waves are moved slowly towards the Earth and then away from the Earth by these gravitational waves. And so the signals will arrive early when the pulsars are closer to the Earth and then later when they're further away.
So is this just the same as the Doppler effect of like an ambulance that's coming towards you and the pitch sounds higher when it's coming towards you?
It's similar. So you can think about it as red shifting and blue shifting, but it's also like the space-time is physically changing by, about 1 meter per light year.
Wow. Okay. So that sounds like nothing, but these clocks are so precise that makes it detectable.
Exactly. It makes it detectable. That's exactly right. And so that's the only way that you can measure these gravitational waves right now is by actually turning our whole galaxy into a gravitational wave detector by timing all of these pulsars. And so if so imagine you go to your radio telescope, you're at Jodrell Bank or you're at the Green Bank Telescope and you're timing a pulsar. You have to go to this pulsar and then you time it for about 30 minutes and you get a timestamp. And then you go back in 2 weeks and you time it for another 30 minutes and you get another timestamp. And you do this for 15 years or for 20 years. And over that time, you'll start to see that your expected arrival time from your pulse is different from your actual arrival time of your pulse. And that's where the gravitational wave signal is. Now, if you see that in just one pulsar, that could be anything. Maybe there's an error in your instrument. Maybe something happened with the interstellar medium. There's so many things that could go wrong. And so we time a whole array of pulsars with NANOGrav. We have over 60 pulsars that we're timing. And with the international community, we have 85 pulsars that we're timing together. And so when you
These are all pretty local pulsars?
They're all within like around a kiloparsec. They're all within our galaxy.
So what's that, like 3,000 light years?
3,000 light years, that's right. There is one pulsar that's not in our galaxy, but it's in the Large Magellanic Cloud. So it's not like it's Andromeda.
A neighboring little galaxy.
That's right.
Yeah.
But anyhow, so this pulsar timing array experiment looks at all of these pulsars to try to see if there's a gravitational wave signal present in all of them, not just in one of them, but in all of them, all at once.
A simultaneous defect in their timings. So yeah, let me just understand a little bit more of this timing. So it's like a clock, but you know, like the tick, 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 and the ticks are not coming in exactly when you expect them to come in. Let's say they get slower. Do they then go back faster again and then slower again? It periodically bounces around some average rate that you would expect for the clock. And if so, what is the rate at which the clock is returning back to its sort of baseline level? What is the time scale of this effect that you're looking for, this variation?
Right. So gravitational waves travel at the speed of light. And so it is, it's going back to these pulsars, which spin around they spin around hundreds of times a second. They have a mass that's 1.5 times the mass of the sun, and they would fit into the island of Manhattan, right? Imagine putting the sun, shrinking it down to Manhattan and putting it in a blender. Like that's one of these pulsars that we time.
I don't know if I can imagine that, but yeah.
Like they're it's really insane objects. Yeah. And so the ticks arriving early is because the pulsar came, that much closer to us. So the gravitational waves travel at the speed of light, and the the frequency of the gravitational wave is set by the origin of the gravitational waves. So that could be a binary black hole, so two supermassive black holes that are merging, or it could be this gravitational wave background.
I see.
So that gravitational wave background is this, superposition from the cosmic merger history of all of the supermassive black holes. And even then, you can bend them into different frequencies because over time they will evolve. And so you'll have more of them at very low frequencies and then slightly fewer as you go to higher frequencies, because then they start merging. So you get fewer sources as you go to higher and higher frequencies.
Yeah.
So
it's like the orbital period of, if it was two gargantuas, it's the orbital period of those two objects around each other that corresponds to the kind of the restoring time for this clock to go back to its nominal ticking level.
The ticking level, I think, if you want to know what the regular ticking level is, it's when you go and you measure it, for 30 minutes. Then any, gravitational wave period that has this deformation power over a decade isn't going to matter over 30 minutes.
Yeah.
But you really start to see that when you have, a full period come in, and then it's going to give you a timing offset of something like 100 nanoseconds over that decade.
Mm-hmm.
But and then you can start over again. So over your 30-minute observation period, you can't really see anything happening. You really have to time it for over a decade in order to start to see that space-time deformation and your clock slowly getting closer and then going back away and then slowly getting closer.
It's interesting on a human level that it's roughly a decade,
right?
Because that's kind of the time scale for doing something ambitious in our lives, but not if it was 1,000 years, we probably would never bother with attempting this. And if it was much shorter, maybe it'd be too fast for us to be able to set it. It's interesting that it's at that balancing point where it's you just have to invest, which you have done in your career.
Yes,
right?
That's right.
And so how long have these experiments have been going for? Decades then at this point?
That's right. So right now I'm part of the NANOGrav experiment, which is funded by the National Science Foundation. And we are, right now we have a 15-year data set, and that should be published very soon.
Mm-hmm.
And that's going to be very interesting for gravitational waves and for gravitational wave background searches for individual supermassive black hole binary systems. So we started with a 5-year data set, and then had a 9-year data set, and then 11 years, and then 12 and a half years. Now we have 15 years. So my colleagues who do the actual timing have been at this for the better part of 20 years. Because, of course, as you know, as a research scientist, you already have to have some sort of preliminary motivating evidence before anyone gives you money. Right. And so they've been at it for a very, very long time, timing pulsars every 2 weeks for the better part of 20 years, and some of them even longer than that. So, my contributions to the field are really developing models of how the supermassive black holes merge and what kinds of signatures we can see in the gravitational waves that tell us about the environment surrounding black holes and how quickly they should be merging, or what's affecting the evolution of their mergers. Are there stars interacting with them? How much gas is there?
Yeah. What would we learn if I showed you a discovery tomorrow?
Mm-hmm.
What would be the first thing that you would be comparing to your models that you'd be like, I want to find out about this? What would be that thing that you'd be looking into?
One of the really important things is understanding how the amplitude of the gravitational wave background evolves as a function of the frequency of the background. So we have a lot of models that tell us, if your binaries are circular, if they're only interacting with gravitational waves, how should they evolve as a function of frequency? So the
orbits are circular.
The orbits are circular.
Yeah, okay.
Yeah, that's right. And so I would want to see, does the measurement actually match this prediction, or are things more complicated in nature? Are the orbits slightly elliptical and elongated? How important is it if the black holes aren't the same mass, if one is 10 times larger than the other? Are the black holes interacting with gas and stars that would have an observable signature at very low frequencies because that corresponds to a very wide binary separation. And when they're very widely separated, then interacting with gas and stars is a much more effective way of reducing the energy in the system than emitting gravitational waves. So gravitational waves are only really important when they're very, very close to each other. But at these wider binary separations or very low frequencies, then gas and stars become very important. So I would want to see, is the spectrum just, a kind of diagonal line, or is it mostly a diagonal line, but then something funny happens at very low frequency? And does that, diagonal line change shape? And what can that tell us about the presence of gas and stars around this cosmic population of supermassive black holes?
It's a classic theorist answer. You look for that which breaks the models.
Yes, I want to break the models. I want all of the simple models to be broken.
I love it. Yeah, they are. I mean, so I have so many questions about this. What would be the sweet spot distance? Like how, you said it's of order of 1 billion solar masses would be kind of the mass of these objects combined together. Obviously, we don't have that in our own galaxy, so this would be an extragalactic object. But how far away is this experiment sensitive to? And what is if you had to guess, like what would be the most likely scale? How far? I guess I'm wondering, are we looking back in terms of light travel time to what we'd call high redshift? Are we looking back to events which happened millions, even billions of years ago? Or are we looking fairly local? What sorts of events are we likely to see?
It would be right in the middle. So yes is the answer to your question.
So all of the above.
Yes, exactly.
Okay.
So if there were a nearby pair of supermassive black holes that were starting their merger process, then if it was within something like 100 megaparsecs, or what we call our local group, then you would have detected it already, depending on the mass.
With LIGO or with pulsar timing? With
pulsar timing.
Okay.
So an interesting fact that really not a lot of people know is that these supermassive black holes will merge before they ever get to the LIGO band. So their frequency evolution will stop at around 10 to the minus 6 hertz. And the pulsar timing array experiment operates at 1 to 100 nanohertz. So this is super low frequency. Why does that happen?
That's confusing. Why doesn't it go all the way up to those same high frequencies, getting very, very event horizons touching almost? Right?
Yeah, the event horizons touch at that, we call this
because they're just so big.
And exactly.
Wow,
at those very low frequencies. Like that's when they merge. They have this thing called an innermost stable circular orbit for any expert that's listening, or ISCO.
Yeah.
And their ISCO frequency is at 10 to the minus 6 hertz. And
post-merger, there's nothing that gets into those higher frequencies. Like you might imagine the two singularities, even once they're within event horizon distances, are going through some complicated gyration and merging process.
Right. So I believe that the super theorists, I'm a theorist, but these people are even one level of abstraction beyond me, call these echoes.
Yeah.
And those might be in like the LISA band, and so still low frequency, but nothing to my knowledge
and LISA is
the space-based gravitational wave detector.
So that's something that doesn't exist yet, but we're hoping to build.
Exactly. So it's been approved. The European Space Agency is leading this project, and NASA is a junior partner. And this will look for gravitational waves from the baby supermassive black holes, and then also a gravitational wave background from the galactic population of white dwarfs.
Okay.
Which is cool.
I always think it's funny when people say LISA, and it's like, who's Lisa? Like, who's this person? She's going to do all this stuff, this one graduate student? Or?
Exactly. Lisa is amazing. But Lisa will only join us in 2034 or maybe
She's
2038.
Still studying
exactly.
In high school right now.
Yeah. Lisa is expensive, and it's taken us a while to get her. But she should be here soon.
Yeah, hurry up, Lisa.
Exactly.
So with all this science, there's obviously this idea of looking for coherent changes between these pulsars to detect these objects. There's a lot of physics about the pulsars, which is interesting as well. So I'm sort of most familiar with pulsars because they were obviously one of the first methods used to look for exoplanets.
That's right. Wasn't the first exoplanet discovered around
Correct.
a pulsar?
Yeah,
Yes.
the first accepted one. There were claims before that ended up being correct, and some that were wrong that actually predated that. But that was the one that we were like, okay, there's no doubt, right? There's no doubt at this point. And so, yeah, that makes me wonder, like, if these pulsars all have planets around them, which probably isn't true, but, you know, there's some companions around them which are wobbling. You might think that's an extra source of noise to some degree from your perspective. That's annoying for you. The planets are just a nuisance for you.
Yes.
And similarly, correct me if I'm wrong, but I've seen some discussion of even the surface topography of these pulsars, of having like we call them mountain ranges, but there might just be micrometer deviations. But even that mountain range could affect the spins. It could cause them to almost like an unstable rotate, to have slight gyrations. How much of those extra complications do you have to worry about? Or does the coherence issue mean you can just sweep all of that under the rug?
This is a very complicated answer. I'm going to go step by step. So number one, the pulsar planets. So those would show up as, for us, it would be a high frequency noise, right? Wherever the planet is for us, for our experiment, given that it has baselines of decades, the pulsar planet would likely have some sort of, would be some high frequency noise. And we don't have a lot of sensitivity in that part of the detector, so it's not a huge issue.
Even if it's very long period, like a Jupiter?
Maybe. I don't know of that being the case, but it doesn't mean that it's not possible.
Okay. Yeah.
The shtick of the pulsar timing array experiment is that you're looking for a common signal in all of the pulsars. And so each pulsar has different noise properties, and that could be planets, that could be some weird deformation. But the common signal that's in all of the pulsars should be the gravitational wave signal.
Because even if they all have Jupiters, those Jupiters aren't going to be all in exactly the same period, at exactly the same phases.
Yes.
That's not going to happen. But it will still almost be like bigger error bars for you.
It'll be noise, exactly.
Yeah.
So it does induce noise. The noise isn't correlated. So the more pulsar pairs you have that you can, look for this common signal in, the better you are at extracting that signal. But noise is a huge problem because our detector, it's the whole galaxy. It's all of these pulsars in the galaxy, and we can't turn the pulsars on and off because we think something weird happened. And we have one data set that spans, 15 years and almost 17 years now, if you include our more recent data. And you can't just like wipe it all away and start over again, without a huge penalty. Yeah. And so creating custom noise models for each one of the pulsars is this new priority within NANOGrav that's really taking off and is really important. And I, even have a graduate student working on this project because there's tons of things that can affect the pulsar arrival times. One of the pulsars is very close to the ecliptic, and you can actually see the solar wind go through the pulsar pulses. And it's really crazy, but you can see these like perfect peaks in all of the pulsar arrival times, and you're trying to model the noise because you can actually see the addition of noise to this pulsar as it gets close to the sun. And as the pulsar beam travels close to the sun, there's all of this additional material for it to go through. And, it's really incredible to see. And that's just one source of noise. But then there's the interstellar medium and changing column densities of electrons between us and the pulsars, even before you get to your very nice example of, the pulsar itself. What do we know about pulsar magnetospheres or emission mechanisms or all of these? It's almost even taboo to say the words because no one has any idea, and it makes theorists shake. And so all of that stuff is big unknowns, but for the sake of gravitational wave detectors, it's not our primary source of noise that we're concerned about because they're so uncorrelated that it shouldn't create a signal. Now, if for whatever reason, we actually don't understand pulsars as well as we think we do, and there is some sort of common deformation that's happening in all of the pulsars, it's possible that we could detect that kind of noise source because it would also be the same in all of the pulsars. And that's really what we're looking for in this array is what's the same signal and all of these pulsars. And so theorists like myself and my colleagues have created models of what that signal should look like. But if we missed out something that's like what's happening at the pulsar, then we could accidentally be picking that up too when we're doing the data analysis, when we're looking for those signals.
That seems so contrived though, because even if there's like the sun has what we call P modes, right? It vibrates, star quakes essentially, like earthquakes, star quakes on the sun. So maybe there's something like that, some kind of gyration happening within these stars. But it'd be so weird if they all phased up. It seems,
it would be very weird.
It just seems like, unless, you know, you have like this Q from Star Trek just playing like a weird trick on us, like some super omniscient being who's just trying to screw us over. How could these disparate regions possibly be related to each other? And so I guess what I'm wondering is, it seems to me from the outside that your false positive rate, which we're always concerned about in science, false positive rate experiments, your false positive rate would be very, very low. And yet what's, maybe we can talk about this there was a recent claim of a possible signal, I think a year or two ago, from data research. Maybe you know more about this than I do. But I remember reading that people weren't convinced yet, right? There was some kind of hum that looked consistent with a pulsar timing gravitational wave signal. People didn't believe it. And I was thinking, well, what else could it be? What am I missing? Like, what are the false positives here? Why don't we claim that is the first detection? And maybe you can give us the backstory of that.
Sure, of course. So this was a really exciting paper. And I completely agree with you that it would be very contrived to have this exact same signal being in all the pulsars. What I'm saying is that it's possible, but I completely agree with you that it's just highly unlikely. I really don't think that that's the case.
Just a statistical fluke, because there's 85, maybe some extreme coincidence or something.
Exactly.
Okay.
And so the false positive rates are computed using a technique called sky scrambles, where you take the pulsars and their positions in the sky, and then you randomize them, and then you say, like, do I see the same signal? And that would be a false positive. And so we have to do a lot of these sky scrambles to establish, you know, the detection statistic and how much you believe things and what's the false alarm probability.
So that's a detector-induced false positive, or is that an astrophysical false positive in that case?
I'm not sure I understand what you mean.
If you do this sky scrambling experiment and you get false positives, are those, is that purely sort of a is that just a chance of sort of the random noise in the data structure almost, rather than the universe itself is not producing a false positive?
That's right. It's in the detector. Okay. And our detector is the pulsar Earth baseline.
Right. It's not like a star quake that are all in phase, or planets that are all in phase.
That's right.
Something with the instruments itself.
That's right.
Okay.
That's the sky scramble. You're talking about cosmic variance, which could be another weird thing that happens.
Cosmic variance. I love that term. What does that mean?
It just means that, you know, what the signals that we predict are this, you know, ensemble average from what we understand, what we think the universe should look like. But of course, we do this over multiple realizations of the universe in our models. So we can come up with, like you say, you know, in one model of the universe, stuff looks like this, and then it looks like this, and then it looks like that. And which one did we actually end up with? Right? We don't know yet because we haven't measured it yet. We know what the average looks like, so we know what the signal should look like. But it's possible that we're in a very weird universe where some sort of contrived solution is just what we happen to end up with. And so what we're trying to understand is, you know, if I see some sort of bump where I think that there should be a flat line, I guess the astrophysical false alarm is in that sense, like, in how many versions of the universes that I modeled did I get that bump, right? And so that's different from the sky scrambles. That's if I randomly arrange pulsars, do I see the same signal? Because it just happens to work out that way. And then the astrophysical one is I've made all of these models of the universe, and you know, what's the significance of this event happening that I think that I see, you know, how many times does that happen on average? So that's your false alarm probability question. So you asked me another one. I couldn't hold the thread.
I'm kind of wondering, we were wondering about this detection. So there was this claim detection.
Yes, of course. This is in the 12.5-year data. And so
do you believe what's going on there? Do you believe this? What does this mean? Where are we at with this?
Right, totally. So the gravitational wave background signal evolves very slowly in time. If you look at what how the signal should evolve. It should evolve as the square root of time and as the number of pulsars in your array. And so what you would expect to see starting out is some sort of red noise, a very low frequency signal that's starting to become this common signal in all the pulsars. And that's what was found in the NANOGrav 12.5-year data. We saw this, signal that was in all of the pulsars that had an amplitude that was exactly what we expected it to be for, to be coming from the cosmic population of supermassive black hole binaries. The same in all
directions as well? Is there a directionality to it?
There is very likely a directionality to it. In fact, that's what a large part of my PhD work was based on. We call it anisotropy in the background, but no one actually needs to know what that word means. It just means that there's more power in one direction than the other direction. And so with the NANOGrav data, there hasn't been anything published on anisotropy in the background. Right now, we assume it looks the same in all directions as a first order
There's
search.
no paper? It's just like a press release or something? Or was there...
Oh, no. So the 12.5-year data, it was a search for an isotropic background. And what we found was this amplitude, that looks like it could potentially be coming from supermassive black holes, gravitational waves from supermassive black hole binaries. But there's a second part to the detection, which we didn't see. And this is a correlation function. So when we're looking for this signal, what we do is that we cross-correlate all of the pulsars in the array. And cross-correlation is when you take 2 time of arrivals and you say, like, what's common in these? Like, can I find what's common in these? And then you take another one, and then you take another one, and you do this with all of the time of arrivals and all of your pulsar data streams, and you look for common signals. So there's 2 signals that should be present when you do this. One is this amplitude of the gravitational wave background, and the second is called the Hellings and Downs curve, or this correlation function. And so that tells you how the amplitude of the background is modulated as a function of the angular separation of pulsar pairs. It means that if you have 2 pulsars that are close together on the sky, they'll have a maximum signal. And as you move one pulsar further away, that correlation drops down so that the amplitude becomes lower and then it comes back up higher at the end. So it has this almost like a quadrupolar, almost like a cosine shape, except the end point is half of the beginning of the first point. So between 0 and 180 degrees on the sky, you can predict how the amplitude of the gravitational wave background is modulated by the geometry of your pulsar timing array.
So what was detected? Maybe I'm simplifying this way too much, but for the sake of a useful analogy to try and get our head around this, there was a hum that was detected amongst all of these 85 pulsars, but you're also wanting to see almost like when 2 singers harmonize with each other and they're correlated with each other when they're harmonizing. You just don't see that cross correlation yet. Doesn't mean it's not there, but just the detector isn't quite there yet with the amount of data it has to see those harmonies between the different stars.
That's right. That's right. So we can't see those cross correlations manifesting in the way that we would expect for a gravitational wave background, but we do hear the hum. So yeah, we can hear the chorus, but I guess we don't know what the shape of the choir looks like.
This analogy's going to maybe stretch a little bit too far.
Yeah, exactly. We've stretched it and squashed it. Exactly. So many mixed metaphors.
Okay.
But definitely, so that's the thing. There was the hum, but there was no Hellings and Downs curve or this additional spatial correlation term in the 45 pulsars that were in the NANOGrav 12.5-year data. And upcoming data releases, if you want to believe that we've actually detected a signal from the cosmic population of supermassive black holes, you need to have those 2 pieces. So you need to have the amplitude and these additional correlation terms. So any detection needs both of those. So the 12.5-year data had part of it, but not the second half.
So you remain skeptical about it at this point?
I am confident that it should be detected very soon.
You probably know more than you're letting on here, I think. So that's exciting. So it seems like we're on the cusp
I would say that that's a very accurate statement to make. Yes, we're
Okay.
definitely on the cusp of detecting the gravitational wave background. And it's also a nice check to say, if you believe that what was in the 12.5-year data was a real signal, how many more years and how many more pulsars should we add to see the full signal, right? With all of the additional correlation terms.
Now, when we got the first LIGO detections of merging black holes, as you said, it was a profound moment in astronomy because it opened up an entirely new way of seeing the universe.
Mm-hmm.
And there is an entire new field of astronomy, essentially, of studying these merging black holes.
Yeah.
In the same way, how would you compare that moment to the cusp moment we're on of detecting these background gravitational waves? Will there be similarly an explosion of interest, you think in these signals? And what is the types of science you can imagine people using this for?
I could talk about that for hours. But yes, so LIGO making the first detection was, like Galileo holding up a telescope and, even just seeing the first photons of light, right? That were far away that you couldn't see with your naked eye. And so what we're about to do with pulsar timing arrays is something very similar, just at a different frequency. So it's like the first radio telescope, someone realizing that light actually has multiple wavelengths or frequencies and saying, wait, there's optical light. So shouldn't there be X-rays? Shouldn't there be radio waves? Shouldn't there be something in the infrared? And so now what we're doing with gravitational waves is saying, okay, we've got one part of the spectrum and we know what's going on over there. That's cool. Let's keep building more telescopes. But now we have a different telescope that we can detect different signals with. So LIGO is great for detecting, stellar mass binary black hole mergers. But with pulsar timing arrays, you can detect supermassive black hole binaries, but you can also detect things like primordial gravitational waves from inflation. Right? At the beginning of the universe, you had these quantum fluctuations in the universe that were blown up to the entire size of the universe. And some of those quantum fluctuations start freezing out at different frequencies. And so you can actually detect them in all of the gravitational wave detectors, which is very cool. You can detect cosmic strings with pulsar timing arrays.
Tell us what a cosmic string is.
A cosmic string is the best definition that I found that I think is understandable was from Wikipedia. And that's, I know.
Astrophysicist goes to Wikipedia to find out. Okay.
For real. But like, it's great.
Good stuff on there,
It's this phase transition in the early universe. And what is a phase transition? If you drop an ice cube in a glass of water and it cracks, there you go.
Okay.
Cosmic string.
Yeah.
So something like that happened in the very early universe. And that string is very, very, very dense. And it's like this, imagine just this dense space-time deformation. And it can make kinks and cusps, and it can make loops. It can interact with itself. And
is this connected to string theory, or is this completely separate?
Some are.
Okay.
Some are. Cosmic superstrings are related to string theory, and other cosmic strings are not. But basically, the cosmic string can interact with itself. It can make a loop, and the loop pinches off and evaporates by radiating gravitational waves. And this is all theoretical. It hasn't been observed yet, but this is another kind of thing that could create gravitational waves. Right. And so anyone who does this very, theoretical high-energy astrophysics is very excited by NANOGrav and other pulsar timing array experiments potentially detecting these gravitational waves, because they would say, look, you found a signal, but you don't know what made that signal. To be fair, that's true. That's going to take a few more years to be really sure that the signal comes from supermassive black holes and not a combination of sources. Some of it could be primordial from, from the Big Bang and inflation. Some of it could actually be from cosmic strings. Like, who am I to tell the universe how it should work? Like, maybe that's actually what happened. I don't know. I'm sure that general relativity sounded very fanciful and exotic to people, when Einstein announced it, and they're like, wait a second, you're telling me that space-time fabric is doing what and curving what and doing what, and why do we need to know this? And this is crazy. But who knows, right? It sounds exotic today, but it's just, I think, because we're not used to it.
I mean, that's got to be a Nobel Prize winning discovery, a cosmic string, that just sounds like one of the most awesome discoveries I can possibly imagine. It's just
Yeah.
and again, that's something that would be totally undetectable with photons, with light. It's a unique capability of gravitational wave astronomy.
It is a very strong capability in gravitational wave astronomy. I'm not sure that I know enough to say that
it's totally unique.
It's totally unique to, pulsar timing arrays. Exactly. But it's also in an episode of Star Trek. And I think that the Q might actually make an appearance in that one too, because Q is the best.
He's a misfit, but we love him. Yeah. Yes. He might be back in the next season, I heard. So I'm looking forward to that. We'll see.
Oh my goodness. This is very important.
Yeah, so we're nerding
I'm so
out
glad
Star
I'm
Trek.
here today.
Any excuse to talk about Star Trek, I'm straight in there. So this is pretty an amazing moment potentially in astronomy that we're seeing all these changes, and I'm kind of curious about your journey in this as well. I feel like we have a lot in common with our scientific journeys and working very different things. We've both been searching for something for more than a decade, or working on searching for maybe not just us, but in collaboration with others. And it's mentally, I've often found that quite difficult, right? To look for something that it's harder to do something completely new than just to do the industrious work of refining that which has come before, right? That's a far easier proposal to write, to say, I'm just going to find more X-ray binary black holes, which is how we were looking for black holes before. Well, okay, we know those exist, so sure, I'll give you some telescope time to look for that.
Right.
But to do something completely new, to build a completely new type of experiment is always more risky. How have you, maybe you could speak to that, like how have you found that journey of risk in your own professional career? And is it exciting to you? Has it been difficult? What's your journey been like?
Wow, what a question. So for me, I guess my mentality was always go big or go home, right? Because this is such an amazing field to be working in. And my options when I started working on, even in astronomy were to, either work on LIGO or pulsar timing array experiments. And I did in a year, almost 2 years of work with LIGO data. And it already felt to me like things were pretty mature. And that was, back in the early 2010s, that there wasn't really a place where I could come in and say, like, I did a thing. And to me, it felt really important that if I'm following this passion of mine to study black holes, that I want to put a flag right in the ground and say, like, I did a thing.
Yeah, to own something of your own achievements.
Yeah, exactly. And so for me, it became clear that pulsar timing arrays had a lot of work that we still needed to do in theory. So I came to my PhD with a master's degree in cosmology. And so in cosmology, a lot of these tools had already been developed to deal with the cosmic microwave background. And I took some of those tools and I imported them into pulsar timing arrays to look for the gravitational wave background and to look for deviations from like this perfect flat isotropic background and to look for anisotropies in it, or little hot spots where you'd have some black hole binaries that are closer than others. And that was completely new, right? And so like that kind of fundamental work still hadn't been done. And then since then, I've really, just tried to have a lot of fun. One of the professors gave me some really good advice at the University of Birmingham, where I did my PhD, and he was an experimentalist, but he said to me one day, he said, Chiara, they don't pay us enough to not have fun. So you might as well just have fun. And it really stayed with me because it's true. I think we have really incredible skill sets, and I think we're all very passionate people. And I think that's what also makes it really hard when it comes to writing grants and having, 99% of them rejected, because like you do have great ideas, but so do all of the other smartest people in the whole world that you're up against. And sometimes it feels so random, when you get your feedback, and sometimes it doesn't even make any sense. And so it's really important to me to feel like I still have an emotional connection with my work, and that I care about it. In the last few years, though, since becoming a professor, I found a huge amount of joy in training my students and showing them how to do what I do, and also to see how they do things, and asking them those questions, and, poking and prodding at their knowledge to see, where they are, and then watching them develop their own ideas, and then helping them on their path with their own ideas. And that to me has been incredibly rewarding as well.
Yeah, and I know from speaking to students that you are a fantastic mentor, so I
Oh,
appreciate that point as well. And it's nice to be able to pass that along, because I think we all got to where we are because of enormous privilege of having mentors who guided us through to that point as well. There's such a lottery with who advises you to a certain extent as to where you end up. And
totally.
I'm so grateful to the mentors I certainly had. Yeah, and so this whole journey you're on, I'm wondering, have you felt that was kind of your own individual experience, but has the field itself evolved in terms of its perception from the broader field of astronomy? I feel like when I first heard you speak about this, I'd never heard of this idea, and it really felt almost left field. And I'm sure people feel that way if they've not heard me talk about exomoons before. Probably, what? And was it almost like a PR battle to get the rest of astronomy to think about, because you're in the mainstream now, it feels like, and it seems like you're about to hit the big time with this field. So how has the broader perception of this subfield of astronomy evolved?
I think that, all of gravitational waves it was very difficult to get people interested in it, especially before detection, before LIGO made the first detection back in 2015. 100 years after,
Einstein wrote down.
exactly 100 years after Einstein. And, even Einstein didn't believe that they were detectable because they were so small. It was almost just like a mathematical curiosity. So it's really taken a huge amount of investment. And, some estimates put building LIGO at something like $2 billion over the 40 years where it was, being funded and operated and upgraded, and all of the salaries. So it's a huge investment. Pulsar timing arrays, on the other hand, are a much newer idea. This idea of looking for a common signal in all of the pulsars was only published in 1983. And even so, that was assuming that the background was isotropic. And then my paper looking for anisotropy came out 30 years later, right? And so the field was, I think, as you're pointing out, not exactly stagnant, but not flourishing. And so I think that it was a PR battle in order to get people to care about pulsar timing, even people in our own community, because my radio astronomer colleagues are all, superstars in radio astronomy timing pulsars. Like they can do so much interesting physics just timing pulsars, that looking for gravitational waves, even for them, was this, corollary. It's like an addendum at the end, like, and I can do gravitational wave searches, but really you can do so much fun stuff just timing pulsars. So it's really taken a lot of time to get people to care about this as an experiment that can actually do really interesting physics.
Yeah, I guess so treating it more like it was the fluff, right? It was like, maybe this is extra thing, and now it's actually becoming the steak, right? This is like potentially the main course.
Exactly.
So maybe just to finish off, because we're kind of wrapping up on time, but maybe you could, you've had this incredible journey professionally, and remember your name, listener, Chiara Mingarelli, because you're going to be, I'm sure lots of people will be hearing about exciting stuff coming out of all these experiments soon. But do you have any advice to astronomers or potential astronomers who are thinking about getting into this field? It often feels like all the cool stuff has been done, right? I remember feeling that way a little bit at college, that certainly in physics, like all the amazing stuff has been discovered. I wish I'd lived 100 years ago or something. It would have been far easier. How do you feel about the state of the future for a young person getting into astronomy, and what advice would you have to them?
So when I think about this, I think about, it was, in the late 1800s, there was this very famous meeting of minds, and all of these men had decided that really physics was done, that they'd figured out everything that there was to know, that this was really the end, and didn't they do a good job?
Pat
And that was
themselves on the
before
back.
patting themselves
Cheers,
on the back. This was before quantum mechanics and before general relativity, So I always feel like we're at that place where, we kind of feel like we've done all the cool things, but like, what's dark matter?
No
Right?
one knows.
No one knows. Like, we know that things look weird, galaxy rotation curves, lots of evidence for something that's dark matter. But what if we're just on the verge of another paradigm shift? That's also a possibility. There's so many questions that no one but these future scientists will even know how to ask. Yeah. And so I think that science is best when it's done by a diverse set of scientists who have different experiences and different points of view, that just see things differently. This is when we really get our best science, is when we're all mixed together, working on projects together. But it's easier said than done, right? There's a huge amount of privilege that even goes into knowing the fact that you can be a scientist.
Yeah.
I was very privileged. My dad is a math professor. So I grew up knowing what a professional research scientist looks like, knowing that I would have to apply for grants and what all that stuff looks like and travel. But some people don't even know that you can be an astronomer as a job. So I hope that people that are interested in that as a career can pursue that path, that they can, talk to professional scientists and understand how they got there. I think I just also want to point out that, professors, most of us, never left school, right? We have been in school our whole lives and we never left. So we're like the professional students and we love school. So please talk to us about school. Because there's literally nothing else that we would rather do. And you all really care very deeply about what we're working on. And so if you know one or if you email one, depending on how busy you are, sometimes people can get back to you and talk to you. So I would tell them to explore what they're passionate about. But, but don't be easily discouraged because it's super competitive. But if you really love it and you stick at it, you can make it, and it's totally worth it.
It's great advice and lovely place to finish. Thank you so much for your time today. And I will have to have you back on because it sounds like there's a lot to come in the near future that I'm certainly very excited to hear about. So thank you for your time today.
Thank you. We'll stretch and squash your mind. Thanks, David.
So that was my conversation with the wonderful Chiara Mingarelli. I hope you enjoyed it as much as I did. I wanted to finish with a final thought, and that was on the idea of persistence, because I think we both have that in common, and it's something that I'm sure you too can relate to. So to give some context here, as I said at the top of the video, Chiara and I have both been looking for two very different things, in my case exomoons, in her case the background gravitational wave signal, two things that we know, or at least have very strong confidence should exist, and yet has not yet been conclusively discovered. And the point of discovering them is not to prove they exist, because as I said, we are almost certain of that. In my case, how could you possibly have planetary systems that lack moons, given how many moons we see in our own solar system? In Chiara's case, how could you possibly build supermassive black holes in the absence of mergers? You can't just start with a black hole that's 1 billion solar masses. There must be a process of merging smaller black holes together to make such gigantic things. So in both cases, the point isn't to prove this thing exists, but rather to characterize them, to understand the process by which they build, they originate, and they evolve. With exomoons, we could potentially discover new habitable worlds, understand the uniqueness of our own moon, the moons of Jupiter, for instance. In Chiara's case, we can understand the spin of these black holes, we can understand the environment in which they sit in, how fast does this merging process happen, and understand really the ubiquity of supermassive black holes more generally. So in both cases, huge amounts we could learn. In fact, one would even say both of them are new windows into the universe itself. Things which currently we really have basically no information about. So, hugely important science. And yet, despite that, dear listener, there is of course, a lot of resistance, a lot of struggles, a lot of obstacles to realizing that dream. Because when you're proposing for telescope time, proposing for funding, and this could equally be for a business as it is for science, proposing to try and recruit people, to try and get students to work on your project or to employ people for a project, it's much easier. It's much easier on the other side to fund, to invest, to engage in activities which are already bearing fruit. So in the case of gravitational waves, that would be to invest in LIGO. And that has clearly been happening. And I don't think that's the wrong thing to do. It clearly makes sense to invest in LIGO. It is discovering dozens of new binary black hole systems and neutron star mergers. We're learning a lot from that. But at the same time, we shouldn't ignore this completely new way of discovering gravitational waves, the background signal, which would reveal an entirely new orthogonal way of understanding the impact of gravitational waves, the messages that are being carried on these waves to us. So that can be hard because it's much easier to go for the short term than the long term, the thing which is already delivering fruit than the thing which promises fruit down the pipeline. We have both, I think, struggled with that in our careers, to convince and to persuade, and yet we are both extremely passionate about why each of our topics are so important for the future improvement of science, for improving our own knowledge, the human race, our understanding of the cosmos. And sincerely, I believe that. I know Chiara does too. And I think this belief and this persistence that you have to have is something which I hope translates beyond just science. In fact, I'm sure it does. I'm sure many of you are starting a business for the first time, are planning out some personal ambition, maybe like a wedding next year against all of the odds or something. You have a difficult family, or maybe you're trying to learn a new skill. In my case, I'm actually learning to become a pilot at the moment. And in the same sense, you have to have a lot of persistence in all of those things to be successful. And it's nice when the story is simple. You turn up in the lab, you get discovery on the first day. Great, that's a lovely, neat, tidy story. In reality, that's not usually how it is. It usually is a messy process, zigzagging, rejections, some progress, then 2 steps back. That's usually how science is. And I think we have both directly experienced that. And I hope that is something that you took away from this conversation, and also took away how persistence can lead to results. Because trust me, Chiara has a result coming very soon. And this podcast is hopefully very well timed for that. So you will surely be hearing her name in the news in the next few months, the next years. Just look out for that. I hope you enjoyed this conversation. If you want to support what we do here, the Cool Worlds podcast, honestly, the best way is to head to our website, coolworldslab.com, and you go to /support, and you can click on there and support my research team. Not the podcast directly, but my research team. If you support the podcast directly, it means I have to spend less time writing proposals, applying for grants, things like this, and it gives me more time to actually work on these kind of outreach projects with you. So that's the best way to support us. And then you can also have some confidence that your money is actually going directly into research. I mean, how fun is that? Your money is supporting real research. In fact, you can even claim it if you're a US citizen as a tax-deductible expense. So you can go through that, a charitable donation, I should say, and you can go through that and fill out the forms, and Columbia will help you with that. So that's our podcast today. Please do look out for future episodes. We have many great conversations down the pipeline. And until next time, stay thoughtful and stay curious.